No, it is not a typo. We are talking about the number e today. So it's a little weird to think about the number e, but we're just going to relate this back to the number pi, right? So pi, just a ratio, is an irrational number. We know pi is approximately 3.14, blah, 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 blah. E is approximately 2.72. So the way that we arrive at e is we take our compounding interest and we're just going to basically say it's going to compound continuously. So if I have this thing 1 plus 1 over n to the n, what is that going to give us? Okay, so if I plugged in an n value of 1, right? So let's say n equals 1. This is just going to be 1 plus 1 over 1, which is 1, raised to the first, will give me 2. Let's say I did it for 2. So now I'm going to say n equals 2. So now when I do this, I'm saying I have 1 plus 1 over 2 raised to the second. And now this is going to give me, and I'm going to approximate here, so we got 1.5 raised to the second. Oh, I already knew that. That's embarrassing. 2.25. And then if I do it again, we get n equals 3. We see that every time we do this, we're compounding more frequently, so the value is going to get slightly higher. And we're going to basically say, okay, well, let's continue doing this thing until we reach infinity. So 3 is the last one I'll show you. Here we got 1 and 1/3, and we're going to raise that to the third, which will give us approximately 2.37. So as we do this and we keep increasing our n value, we're going to get closer and closer to this value e. So I don't expect you to be able to derive this exact answer yet, but maybe later on in your math career. So here, as n approaches infinity, we get our value of e, which is approximately 2.72. So this is going to get used whenever we want to continuously compound something. So there's a difference between doing it periodically and doing it continuously. If I'm continuously doing it, it means that every fraction of every second is going to have a split increase on it, and I'm gaining interest on that interest, or growth on that growth, if we're talking about like a population or whatever. So let's just look at a couple examples of how we use this e number, because it really is just a number. There's nothing crazy about it. There's nothing different than anything we've done before. So we're going to represent it with e, just like we represent pi, pi, as the symbol here, right? So we're just going to leave it as e being a number, which is approximately 2.72. So when we look at this expression, if I have a base to an exponent times the same base to an exponent, I'm going to add my exponents. So here I'd have e to the 7th. Oops, that's not a good circle. There we go, that's better. And you could come up with an approximation for this, but we really just want to leave this as e to the 7th. Here I have 10 over 5, which will simplify to 2 on top, and I have a 1 on the bottom. I have e to the 3rd on top and e to the 2nd on the bottom. Top is bigger, it's going to win in the end. I'm going to cancel off 2 of my e's. So I cancel off 2 of my e's, I'm left with e to the 1st. 2e over 1 is just going to be 2e. For the last one here, I have a thing raised to an exponent. Now, when I have it raised to an exponent, I want to make sure that each of the pieces are getting the exponent. So here I'm going to have 3 squared times e to the negative 4x squared, and I'm going to write this like this because I have an exponent raised to an exponent, and I want to make sure I do that correctly without leaving off the fact that we have to also square our 3 value. So now as my next step here, this is going to equal 9 times, and now this is e. Now exponent raised to an exponent means I'm going to multiply these things to the negative 8x. If I want to rewrite this thing without a negative exponent, then I would rewrite it like 9 over, and now here I have e to the positive 8x. So same as all the different things we've done so far, just now we have this new number e. We want to talk about how we evaluate e. So there's 2 different routes you can go depending on what calculator you've got. So I'm going to start out with the TI-30. So this is a kind of simpler version of the calculator. There's a button on the top left. If you hit second and then it says e to the x, it's the ln key. So if you do second and then you hit that button, it's going to automatically be raising it to an exponent. So if you just wanted e as itself, then you just say raise to the first, and it'll give you, the approximately 2.72. So when we're looking at this, that's one route to go. With the TI-84s, or 83, whatever you've got, there's two ways of doing it. One is that there's an E key. So if you want to do second and then you hit the division sign, that's the E in blue there above. And then you can also do second, and on the bottom left, if you use the LN key, you see E raised to the X. So in that case, it's the same as the TI-30 calculator, where it's automatically going to be raising it to an exponent. 8% of the time, we're going to be using E to some exponent. So that's typically what we'll go with. But if you just want to use the second and then hit the division sign for the just E, you can do that as well. And you can always just raise it to an exponent too. So both ways on the 83, 84s are going to get you to the same spot. So here we want to evaluate these things. If I have E to the second, I'm simply going to hit second, hit that little E to the X button, and then I'm going to hit 2 and just hit enter. And it'll give us approximately, 7.38. We'll call it approximately 7.39 actually. And then looking at another instance here, just raise it to a negative 0.06. So same keystrokes, hit that negative button, which is different than the subtraction button. So again, the negative button is in the bottom row right next to enter, and the subtraction button is on the far right in that column. So just make sure you're using the actual negative sign, not a subtraction key. So subtraction key will do subtraction, versus negative obviously turns the thing negative. That'll give us approximately 0.94. Looking at our exponential growth and decay, all E is it's a number bigger than 1. So when I'm looking at this, the only big takeaway that I have for anything different than we did in the past 2 days is that my B value here, well, I'll do an approximation, so equals approximately 2.72. That's it, right? When I'm using E, that's all this is. So all I'm saying is that if I've got E to the X, that's going to give me growth. And if I have E to the negative X, that's going to give me decay. So that's all there really is in terms of a difference between what we were doing before and what we're doing now. Again, with these, especially with these, I'm just going to be rounding to hundredths place. There's no way I'm going to get, nice E values that are going to give me anything nice in terms of fraction or anything like that, because E is an irrational number. So these are just the graphs illustrating these two things. So exponential growth with a positive exponent, exponential decay with a negative exponent here. Still set them up and solve them all the same way. So I'll just do one of them here because they are literally the same thing. Here we have a negative exponent here. Just keep in mind that we have to distribute this. So this is actually negative 0.5x, and then we have plus 1 here. So just keep that in mind, just a slightly different way of representing that. So looking at this first one here, we'll take a peek at this, where we are using our A value is 2, our B value is E, our H value is 0, our K value is 0. So again, all the same stuff that we were doing before. So I'm going to start with H, comma, A plus K, and go from there. So this is going to start at 0, comma, 2. And then from there, I'm going to again pick points to the left and to the right. So I'm going to go X, Y, 0, 2 is right in the middle here. So I'm going to do a negative 1, negative 2, and then 1, 2. So again, I'm going to plug these numbers in. I'm going to use a graph calculator to make it do the work for me. One clever way of doing this is just hitting Y equals and graphing the function. So here I would enter 2, and then E raised to the, what we got, 0.75x. So one thing I guess I will call out explicitly here is that we didn't talk about there being a value in front of the x. So like when we were writing the equation out before, we were saying y equals a b to the x minus h, and we got plus k here. This actually is like another variable, so I don't know, we'll just throw another variable, we'll call it z in here. Z doesn't get used enough. So looking at z, the reason z doesn't get used is because it looks like 2, so that's why it doesn't get used. So looking at z here, this is going to affect how this thing is opening. It's going to affect whether it does it a little bit faster or slower, and if it obviously is negative, then it's going to turn my exponent either positive or negative. So looking at this, that's just going to affect how this thing happens a little faster, a little slower, and that'll actually tweak this thing more than the a value does. Although the a value will affect where it's going to be like positionally a little bit more, like the starting point like this. But overall, this will have a much larger impact. So this is, again, fluctuating much faster as it's dealing with an exponent. So big takeaway here, you can have other numbers in here with the z, and that's just going to represent like this negative 0.05 here and the 0.75 here. So if I did this just 2e to the x versus 2e to the 0.75x, the 2e to the x thing would just shoot up a little bit faster. That's all that's happening. So jumping back into this, I'm going to enter that into my calculator, and then I'm just going to say, okay, I want to go to second, and I want a table set. I'm going to start my table at -2, but you can start at 0 most oftentimes and then just scroll up or down. I'm going to go to second table, and then I'm just going to look at the values for this thing, and I'm going to fill them in. So I get 0.45 approximately here. We get 0.94 approximately here. See, for 1 we get approximately 4.23, and for 2 we're going to say 8.96. So again, just finding these points here. I'm not going to be able to fit all of them, but let's see if we can fit the 2.3, 4, 5, 6, 7, 8. Here we go. So I don't know, it's somewhere a little bit north of that, between 8 and 9 here, but there we go. So there's one more point. If I were to include the -1 point, it'd be at 0.94, and if I were to include the -2 point, it's at 0.45. So let's talk about the domain and range of this thing. So again, my a value here is positive, so this thing is still going to be opening up. So for my domain, I have all real numbers. For my range, it's going to be y is greater than, and here's my k value, so this is 0. So we see this thing flattening out towards 0, but it'll never dip below. I don't know. I mean, I guess I could do this one out as well. It's already right here. The steps are all the same. So a value here is just going to be 1. There's nothing sitting out in front. My sort of z factor, which is changing this thing around a little bit, is going to be -0.5. I would just distribute this. So I have -0.5x, and then I have +1 here, and then I have +1 on the outside. So my h value ends up being -1 from here, and then my k value ends up being +1. So it's actually going to shift this thing to the right one, and it's also going to move it up 1. So we see that happening here. When we look at this graph, there's a couple different ways of doing it. I personally don't graph it like this, but again, you do you. The reason they have it moving 2 over like this is because they don't distribute it. So I'm going to just rewrite what I'm talking about here. So I would rewrite this as y equals e to the -0.5, oops, x, and then here we have +1, -1/2 times -2, and I got +1 on the outside here. So this is actually going to end up shifting this thing, but the way that it gets shifted is a little bit different because this x value is -0.5. So this is going to change this thing. I again would just start from my h comma and then a plus k. So as we're looking at this thing, I would start here at -1, and then I would go plug that value in. It's going to give me 0 here. Going to be +1, so I would start at -1, 1, and that's just where I would start this thing. 0, 1. Hold on one sec here. Let me plug this value in. Let's get rid of this red stuff, and we'll do this green stuff. I'll do it out. Why not? I've at least slipped up in my verbiage once, so might as well do it out. Oh, it's because my starting point changed. Okay, so the thing that makes it a little bit more complex here when I have like a z number or whatever out in here is I'm trying to get this thing to 0 out, but to make this 0 out, I'm gonna have to solve for where this thing is gonna be set equal to 0. So this is going to actually change. I can't just say, okay, it's gonna be whatever the h value is, because now I have a term with my x. So the reason it worked out here is because it's just 0 times a number, but now we have some addition and subtraction. So I'd actually want to set this thing equal to 0. So -0.5 x minus 2 equals 0. I'm going to get x equals 2. So that's actually going to be my h value. So this is going to start at 2, comma, and then I would plug that in. That's going to give me 0. Now I have 1 plus 1. That's going to give me 2. So there we go. My starting point is 2, 2. And then from there, I would plug in, my other points and do the whole thing. So I'd start at 2, 2. To the left, to the right. Here's my x's, here's my y's. So I'm going to include 1 and 0, and also do 3 and 4. So when I'm graphing this thing, this one came out as 2. Again, we're just going to approximate these points. So we're going to go to the hundreds place, and we'll call it good enough. So we're going to change our little formula here to negative 0.5 x plus 1. And then we got a plus 1 on the outside. So be careful when you're writing this to wrap this in parentheses if you did want to put this in your calculator and evaluate that way. And so now we get our 0 value, gives approximately, call it 3.72. Our 1 value gives us approximately 2.65. 3 value gives us approximately 1.6, and then we get 1.37. So those are all of our values here. As we go off to the left, obviously increasing exponentially, so we're going to shoot up to positive infinity there, and here we're flattening off towards the k value. So the way that I look at that is I get a horizontal asymptote at y equals k. My k value here is 1. So now as I'm looking at this thing, my domain is going to be all real numbers, and my range is going to be y values greater than 1, because I have a positive a value out in front here. And that is a couple more of the interesting version of graphing. So nothing is different. Plugging into a calculator, I guess, is slightly more recommended than it was before. Although, again, if it says round to hundreds place before, again, that's all I'm looking for. So, again, I would just encourage people to jump to the calculator sooner rather than write like a final answer here. I'm definitely not going to be looking for these as exact numbers. So here are just our approximations. Here's where we start getting into the real life application. So now is when we talk about like, well, when will something continuously compound? So maybe I have an interest account, which is continuously compounding. Maybe I have a population, which is continuously compounding. There are two distinct ways of looking at this. One is when I have something which is increasing periodically. So this one right here is increasing periodically, okay? This one here is compounding continuous. So as I look at something, I'm going to either have the wording say it's going to increase, n times per year or n times per day or whatever it is, versus I'm going to literally see this phrasing, continuously compounded interest or continuously compounding population. So when we look at this, first question here, number 4, we just want to figure out what boat we're in. Are we in the continuously compounding or not? Annual interest compounded continuously. So we are not going to be using this old formula. We're going to be using our new continuous formula. The new continuous formula is A, the amount that it will accumulate to, equals PERT, P the principal amount, and then E raised to the interest rate times T, time. So this is just the number of years. So A equals PE to the RT. So this is going to be my accumulated amount. I get my P value, which is my starting amount. E is just E, the actual number, so that one is not like a variable that I'm plugging in for, it's just the number E. R is my interest rate, and then T is my time. So for this one, let's look at $1,000, 8% after 1 year. So this is going to be A equals 1,000 e to the 0.08 times 1, which will give me approximately 1,083.29. A little squish there, sorry about that. So again, it just looks like this, and if I had like 5 years, this t value here would be a 5. If it were 20%, then this, instead of being 0.08, would be 0.2. If it were $2,000 to start with instead of 1,000, this would be 2,000 here. So very, very similar to what we were doing before, but now it's a new formula, P e to the RT. So deposit this amount, compound amount. Yep, cool. So now let's look at one more example here. So here we've got some wildlife data. So Fish and Game has kept an endangered species list for these years modeled by, and then here's the first thing we actually care about is this. So when we're doing this, the year that you're using is actually going to start at year 0. So the thing that people get most confused on is that 1972 turns into 0. That's my start. Okay, so this is actually going to start in 1972, and it's going to be increasing. So what was the number of endangered species in 1972? So in 1972, I'd plug in a 0 here, and it'd be 119.6, and then times e to the 0.0917 times t, which is 0. This is just going to give me 1, so it's just going to end up coming to be 119.6, which will just round to saying it's 119. The reason we round down here is because if I had like 0.6 animals, I would not call that a full animal. I would round that down. So when we look at this first one here, it's basically just saying, okay, well, this thing started out with approximately 119. Now the book rounds to 120 here. I'm not going to be a super stickler for which way it goes rounding wise, but typically we round down for impartial things. So if you want to say it's about 120 endangered species, sure, go for it. Graph this thing. Again, just a messy graph. You can do it on Desmos, graphing calculator, whatever. I'm confident you can do it. It just ends up being big numbers, so okay. And then the third part of this says use the graph to estimate when the number of endangered species reaches 1,000. So in order to do this, I'm basically just going to have two equations. One is going to be y equals, and it's going to be that thing. And the other one is going to be y equals 1,000. And then I'm just going to go to second, and I'm going to go to calc, and then I'm going to go to intersect, and I find where those two things cross. Or you can kind of scroll around and get pretty close. So when we are doing this, we get an answer of approximately 23. So the 1972 plus 23 will bring us to 1995, which is like when the expected number of endangered species will reach 1,000. But the real takeaway that I want you to know here is just that we will eventually get to a point where we're able to figure out this value for t. So right now, we don't know what this is, or we don't know how to solve this, but all this is saying is 1,000 equals 119.6 e to the 0.0917 t. So the 0.0917, that's the growth rate. So here we're saying it's growing by 9.17%. And so now and that's compounded continuously. So as we look at this thing, we're saying, okay, well, if I wanted to solve for this, I'd first divide, then I have to figure out a way to get this t by itself. So I have to like un-e this thing, and that's what we're going to get to next. So as of right now, this is more of just like an introduction to what we're going to get to next, trying to show you that there is a need for us to be able to solve for this time value. And that is the number e.